So I will give a quick intro of myself. As Garrett said, my name is Darren Sargent. I've been in software engineering for decades. I have the gray beard to prove it. And I've done all kinds of languages, C, C++, C#, Java, even things like Visual Basic that I don't usually admit to. Mostly it's been back-end development. I did get into big data for a few years. That's my cat in the background, in case you're wondering. And last 3 years, I've been working with an AI team. So I always say I'm not an AI expert, and I don't even play one on TV. I kind of just hang around with AI people, and I've learned quite a bit from them over the last 3 years. So that's my background. I'm going to go over a demo with you today. And as Garrett said, please feel free to jump in with questions. If it gets too off track, we'll have to postpone those to the end, but I'm happy to take small diversions on the way. Just quickly, let's do a couple of show of hands things for those that have turned on their cameras. How many of you know what a neural net is? Like some idea? Yeah, couple, yeah. How many have used Keras? TensorFlow? TensorFlow? Any takers? How about Python?
And Python, yep.
Yeah, a lot more for Python, as I expected. So that's good to know.
Darren, one thing, can I interject? I forgot to mention we're recording the video, so just wanted to let everybody know that we may share that later.
Oh, absolutely. And by the way, anything in chat gets recorded as well. So if you type questions or insults or political or anything like that, it all gets part of the recording forever. So
don't be shy, but be nice.
Exactly. Yeah. So what's next? I wanted to talk a bit about the tools I'll be using for this today because people are always curious about that. Let me share my screen so you can see. Share screen, desktop. Can you guys see it? Can I get a thumbs up? You can see my screen. Thank you. So what I've done is create a virtual environment for Python. You guys may have heard of VEMs or virtual environments. It's a way to run a Python program in isolation on your system, so you don't mess up your system libraries by installing weird dependencies. They all get kind of corralled into this sandbox. And the way I activate it is like this. So it looks like nothing happened, but now if I say, which Python are you running? It shows me this custom one, as opposed to the usual, like if I'm in some random command prompt, that's the system Python. So I'm inside this virtual environment here, and I've already installed the dependencies for today's demonstration. I created this requirements text file. And by the way, I've uploaded this to GitHub, and we'll share the URL at the end, so you guys will have access to browse through this. You can still hear me okay, right, over my kitty meowing? Good.
Yep, we're good.
So this is called a requirements file in Python. This tells you which requirements you need for your project, which libraries, which versions. So we'll go through these when I go through the code, but just know that this thing exists. And in my virtual environment, if I say pip freeze, pip is a Python package management tool. It shows you all the things I've installed. So there's like TensorFlow in there. There's Keras. And as far as IDEs go, I'm using this PyCharm, also called IntelliJ. I prefer it. There's plenty of other things you can use for Python. Thumbs up from Michael there. Real data scientists, as I say, I'm not a real data scientist or an AI guy, tend to use a thing called Jupyter, which is it's like a virtual notebook where you can try out experiments and plot graphs and walk through things interactively. My background is a software developer, so I tend to use this IDE because that's my weapon of choice.
Hey, Daryl, over in the SAP space, they now have Juniper for SAP HANA so that you can actually run that, so that Jupyter stuff just keeps expanding.
Oh, a custom version of Jupyter, huh? That's pretty cool.
Oh, yeah. Running on SAP's HANA database using, let's say, a less number of options than you're used to.
Right. Well, that's pretty cool, actually. I hadn't heard of that. But yeah, data scientists and AI types love Jupyter. It kind of resembles writing down equations in a notebook like a mathematician would. I think that's why they like it. But I'm a software developer, so my background is debuggers and things like this. So what are we going to do today? Today, I'm going to give you the old chestnut of AI problems, which is the MNIST database. And it consists of a whole bunch of handwritten digits. Let me show you what it looks like. And you can imagine this might be used by, say, a bank wants to write a system to recognize numbers on checks, like handwritten values on checks or something like that. Maybe they'd want an AI to do it. So this is a really simple problem in AI. It's solved. We get high accuracy on it. And it's kind of a benchmark. When you read white papers nowadays, they'll often refer to MNIST and they'll say, by the way, here's how our new ultra secret algorithm does on MNIST. And everybody immediately knows what they're talking about because everybody has done this. So that's what we're going to do today. We're going to use this database and we are going to create a neural net that learns how to recognize these handwritten digits. Okay, so far? Actually, I'm going to minimize the camera. Great. I'm going to minimize the camera. In fact, now you've all seen my handsome face. I may try to turn off the camera to grab some cycles back because Zoom, as we've been saying, sucks up CPU cycles. So you can no longer see me, but hopefully things will be a bit smoother now. And today we're going to create a neural net that recognizes these digits. For those that are thinking, what the heck is a neural net? It's one of these. Neural nets, I don't really have time to go into the details, but as a quick summary, it mimics the structure of your brain. Your brain has neurons and axons and dendrons that connect the neurons. And when you look at something in the real world, these neurons start lighting up. And eventually your brain comes up with a conclusion, like this pink circle here, like, hey, it's a cat. And how did it know it's a cat? Because these neurons have been trained by you seeing previous images of cats and your parents pointing at things in the world and saying, that's a cat. So your biological neural net was trained to recognize cats. We are going to create a neural net like this and train it to recognize handwritten digits. So there's a few interesting features here. There's the input layer, which is where in the real world, this is the photons coming to your eyes of the cat. In ours, it's going to be the pixels from the images of the handwritten digits. And there's a couple of these hidden layers. The terminology is kind of archaic from the 60s, but I don't know why they're called hidden layers. There's nothing hidden about them. This is where the processing happens. And then you have the output layer, which is ding, it's a cat. Or in our case, ding, it's a written digit number 5. So that's a neural net. And I want to start walking through the code now. There we go.
Hey, quick question, Darren. Have you used the Google Playground where it has the visualization of neural nets?
I haven't, but we're going to do that a different way.
Okay. Yeah.
So yeah, good question. I like visualizing neural nets as well. It helps me understand what they're doing, and we will do a visualization as part of this. But I haven't. You're talking about the code collab, that Google online IDE?
Well, it's just like the diagram you showed where you can visualize, change the weights and measures to dial and the different layers and see kind of like a result.
Oh, I know the one you mean. Yeah, that's very cool actually. Yeah, and you can change the activation functions and all kind. Yeah, I've played around with that a bit too. So that's cool. I
have a real quick question, and I'm very new to all of this stuff, but in neural nets, you have to define the function of the layers. Like I'm guessing that one layer would try to define boundaries. I mean, do you actually program in those different layers and what they do?
That's a really good question, and it kind of gets the heart of what neural nets do. So who is it that asked that question? Your name, sir?
My name is Ken.
Hey, Ken.
Ken. Hey, Ken. Thanks for the question.
Sorry, I came late. I've been Zooming since 7 a.m. this morning.
Oh, I feel for you. I Zoom 8 hours a day, almost every day. So the question was, in case anyone didn't hear it, do you have to define what the layers do and their function? You have to define what type of layer they are. So is this an input layer? Is it an output layer? Or is it a hidden layer? And what kind of activation function you want to use for that, for each node in the layer. But you don't have to say, say you had a neural net for detecting cats versus dogs, you never have to say this layer is for detecting ears or this one is for detecting teeth. We would consider that kind of cheating because the whole point is the system learns how to detect those features. It's not up to you as the engineer to bias it and tell it how to detect each piece of the image. It's up to the neural net to learn that from the training data. So that was one of the big paradigm shifts to neural nets. Rather than you programming in the rules, which is what we used to do back in the good old days before there were pandemics and things like that, we used to write a set of declarative rules, like if you want to detect a cat from an image, look at these features. Instead, you give the net a bunch of training data. You say, here's a bunch of cat pictures, and here's a bunch of non-cat pictures. It may be hot dogs and lampposts and cars, but I'll tell you they're not cats. And it's up to the neural net to rearrange itself so that it can recognize the difference. But you never tell it, first go look for ears in this position and look for this type of eyes, because that way it's not learning. Does that answer your question?
Well, the question was a little more basic. I mean, like, do you have to show it how to detect edges, you know, or things like that?
Right. Okay. So, yeah, in answer to your question, no, you don't have to show it that.
Okay.
You can have different types of layers, and wink, wink, as AI engineers, we know that some types of layers are better at things than others. So we tend to stack the deck and, oh, let's put in a convolutional layer here. Don't worry about what that is. It's a type of image processing. So we do stack the deck a bit, but in general, we don't go to that level of detail that you're describing, and nor should we. We want the network to figure that out for itself. Make sense?
Yeah, that's better. Just one thing that would be great, and don't take any more time, but maybe if we can somewhere post a link to, you know, kind of definitions of the different types of layers, that would be great. Thanks.
Absolutely, yeah. And you'll see some of that in the code that I'm about to walk through. So hopefully that will give you some idea. So yeah, in the interest of time, let's start walking through this code here. You guys can see this, right? Thumbs up, thank you. So like any Python program, here's my imports at the top. Here's the libraries I'm using. So I'm using Keras, which is a very popular machine learning library, open source, like most things nowadays. And I'm using Numpy, which is basically mathematician's heaven in Python. It has every mathematical function and stats function you could ever dream of. It's basically whatever you want to do in math, there's a one-liner for it in Numpy.
Yeah, we worship that. We worship it.
As you should. Well, anyway, and under the covers, I'm using TensorFlow here. So you don't actually see TensorFlow in the imports, and why is that? Because Keras hides that from you. So let's start walking through this. I'm going to walk through this in the debugger just so we can step through each thing and look at things and just play around with it a bit. So I've launched it in the debugger. It takes a while to load up. So what are we going to do first? We're going to load in our training images. You guys remember I showed you what those look like, right? Like this. There's like 60,000 training images. Training labels, what on earth are training labels? Training labels are the correct answers. So when you're training it, you help out the neural net by telling it the right answers. Just like when a teacher is first teaching a subject at school, they'll give some examples and give the answers to the class. That's how we train our neural net. We treat it like a child and tell it, here's a bunch of digits that you're going to be asked to recognize. And while we're training you, here are the correct answers. So it learns to optimize itself to recognize those. We also have test images and test labels. Now, what are they as opposed to training? These are, let's use the school analogy again. These are like the end of semester tests that the teacher gives you. These are examples that the network hasn't seen before. If we only ever asked it to recognize things it's seen before, it could cheat, right? It could just learn to, it could basically just be like a lookup table where it just remembers which ones are which, and it hasn't really learned anything. It's just memorized the data set. We want it to be able to recognize things that it's never seen. So in the wild, when someone gives it a check with some scrawled handwriting, like maybe a doctor wrote it or something and the digits are illegible, we want it to be able to recognize those. So we hold out, this is called holding out some of the data set for testing. So we train on these ones, and these are the ones, the end of semester test that it's never seen. So next step is to normalize the images. Now, what the heck is normalization? This is very common in machine learning. And the reason we do this is for mathematical reasons that to do with calculus that I won't torture you with today. It works better if your input values are in a small range. So supposing you were training on demographics data, right? You have a bunch of information about people. You might have heights and weights and salaries and all other kinds of things you're not allowed to talk about. The ranges of those values could be very different, right? Someone's age is probably going to be between 1 and 90, and their salary might be between 10,000 and 500,000. Those are very different ranges, and it turns out that if you train on that data, it will work, but it will take longer to converge, as we say, to come up to settle into a pattern. So it behooves you to scale your data so everything you're giving it is scaled from in a small range, and the same range for each of the features you're using. In our case, we just have image data, and each pixel is between 0 to 255. Like, think of a grayscale where 0 is completely black and 255 is completely white. Back to this guy. So each pixel, these are 28 by 28 pixel images. And instead of 0 to 255, we're going to scale them. So by doing this, we scale them into -0.5 to +0.5. If this makes no sense to you, just look at it that we're scaling down the inputs so they're all in a nice, comfortable range to make it easier to train. Okay, flatten the images. This is another common thing we have to do. The images in the original training set are in two-dimensional arrays, 28 by 28. So there's thousands and thousands of these images that each is a matrix of 28 by 28 pixels. And again, for optimization reasons and simplicity, it's easier if we can kind of unwrap each image. Think of pulling a thread on your sweater and pulling it and pulling it and pulling it. So eventually you just have one long thread. That's what we want for each image. And that's what this Numpy reshape thing does. Instead of having 28 by 28, we have a 784 bytes of image, like that long thread from your sweater, each byte between -0.5 and 0.5. So before I do that, let's look at one of the images. I have this little function here called view image. I'm going to say view image, train images 0. It'd help if I use the right kind of parens. So can you guys see that little window that popped up there? This is a 5, right? So your human neural networks just recognize that as a 5, so good job, you've been well trained. Let's pick a different one at random. I don't know, 78. What the hell is that? It looks like a 1 to me. So that's how the images look, yeah? Sorry, Garrett?
Yeah, looks good.
Okay, glad you can see it. So we're going to flatten those out. That's why I displayed them before, because my little display thing wants a two-dimensional image, and now we've just flattened them into one-dimensional single thread of your sweater images. So this just prints out the shape of them. Where's my console? I'll do it here. Shape is a Numpy function that tells you the dimensions of your array. So this is really just telling us you have 10,000 images and each of them is 784 bytes of information. When you're doing machine learning and data science, it's really good to do this shape kind of thing to make sure the data is what you expect. So if these numbers were something else or they were the wrong number of dimensions, I would be scratching my head at this point and wondering what I'd done wrong. But luckily, it's correct. There's 60,000 training images, those little black and white things, and each one is 784 bytes. Okay, so what have we done so far? We've ingested our data. This is very typical of a machine learning pipeline, by the way. This is a toy example, but when I'm actually doing my real job that I get paid for and customers pay us to do, we're doing these same kinds of steps, just on a larger scale and with added complexity. But if you were to drill down, you'd see this same stuff happening. Any questions so far, by the way? Feel free to dive in.
Daniel, I was going to say that, do you spend most of your time trying to munge the customer data into something that is recognizable, or do you spend most of your time trying to create the intelligence?
See, this is how I can tell somebody that's actually been in the wars and done this, because you're absolutely right. We spend probably 80% of our time beating the customer data into shape and getting it in a form that we can use, asking the customer for extra fields that they didn't provide, asking them how to interpret certain fields, or, for example, if they give us multiple data sets, how do we link these together? What's the joining field between these? And which are redundant, which columns do we actually need to use? So yeah, the dirty secret of AI is 80% of it is just beating up on customer data until you have something you can use. The other 20% is building your model, machine learning and training and inference. But yeah, that's the dirty secret. So good observation. Anyway, let's continue. We have our data, we've beaten it into shape. We didn't really have to do much for this because it's meant to be a toy example. Now we're going to create a model using Keras. And when I say model, I mean neural network. So to remind you guys, this is this thing, and it's what you have between your ears as well on a much larger scale. So the way you do that in Keras is this thing called sequential. I don't know if we have doc. Linear stack of layers. Control Q in PyCharm gives you the doc on whatever your mouse is over, by the way. So we're building a simple neural network, which is a linear series of layers. And to relate it back to that diagram that I keep showing you, these are the layers, okay? We have an input layer, 2 hidden layers, and an output layer. In our neural network, we have our input layer, which is dense. I'll explain that in a minute. And it has 784 bytes of input. Why is that? Well, you guys saw that we flattened our images into a long sweater thread of 784 bytes, helpfully named it input. And activation equals ReLU. What the hell is that? Well, ReLU stands for rectifier linear unit. And it's a very common function we use in our neural networks. Basically, this defines which mathematical function we will use to calculate whether a neuron should fire or not. That's kind of a mouthful, right? So imagine these aren't just numbers coming in from the inputs, right? Like think of them as the pixels in that image. This guy is going to activate to some degree. Often we say it's between 0 and 1. 0 means doesn't activate at all. 1 means it's lit up like a Christmas tree. What determines whether it's going to activate? It's these values coming in from the input. And how do we combine those values? Well, we could just add them up. We could multiply them. But luckily, researchers for the past 50 years have been working on this kind of thing. And they've told us that there's some functions that work better than others for combining these. And it turns out that ReLU, it's a really simple function. Like if I showed you the graph, you'd laugh and say, really, that? But it turns out to be really useful for neural networks. So this is really just part of the secret sauce in our network. It determines which mathematical function we're going to use to determine whether the thing lights up or not. So that's the activation. I gave you the input shape. 64 is the number of units, hidden units. So that is, you see this mesh between these layers here where this kind of internal computation happens. There's a bit of an art in choosing how many units to have. So in this case, we have 4 units here, right? So this is hidden units equals 4. Here we have 64. How do we know it's 64? This is another dirty secret of AI. There's a lot of art involved in designing your network architecture. And you kind of have to be an experienced AI engineer to get this right. And in practice, what they usually do is try a bunch of values. They'll try 8, 16, 64, 128. They'll run a bunch of training and, okay, which one works best? There's a whole open area of research to do this automatically, because you might be thinking, hey, that sounds like something a computer could be doing. Why can't we just ask the computer to figure out these values? And we're trying to do that. It's called network architecture search. And there's a bazillion white papers published on how to do this. It turns out to be a difficult problem, and humans are still kind of better at this for now. A human network designer that with a lot of experience will tend to come up with a better network than an automated system. So that was our input layer. We have this hidden layer, very similar. It's dense. What does dense mean? That means that everything is connected to everything. If you ever played that game Cat's Cradle with the strings, where the strings connect between your fingers, this means that every unit is connected to every other unit. again, there's a lot of theory behind when should you have it dense, when should you not have it dense and not connect everything to everything. It turns out for this simple problem, just having everything connected to everything works pretty well. And then we have our output layer, which is also a densely selected layer. Back to our diagram, this is our output layer. And this is kind of the conclusion of the network. This is where it tells us what it thinks the digit is. When you give it a handwritten digit, this is where it tells us which digit it thinks it is. So I just named it output layer. It's only 10 units. Why is it 10 units? Because there's 10 digits. And in fact, it's going to give us a probability for what it thinks the digit is out of each of those 10. So you might think that it would just be one value, like tell me it's a 5 or it's a 6. But that's not how neural networks work. It gives you a probability for each one. So if it was a cat or dog classifier network that tells you if a thing's a cat or a dog, it would say 90% this is a cat, 10% is a dog. For the digits, it might say 80% this is a written 5, 5% it's a 2 because they look kind of similar, and percentages for the others. So softmax is a way of converting those probabilities, converting the outputs of the network into a series of probabilities for each digit. So let's do that. I'm going to compile the network, which is, I have a missing import, looks like here. There we go. Actually, I may have to restart. I'm going to restart. I had a missing import on this function. Pretend nothing happened right there. I'm just going to rerun this thing until it gets back to this compile stage. So
this
compiling
is not the code you were looking for, yes.
Yeah, I was messing around with it just before the call and I removed an import. So we're going to compile the model, which means we're going to tell it which optimizer to use. Again, this is part of the Keras secret sauce for when it's training. Which loss function we're going to use. Again, bazillions of white papers on which loss function you should use and which metrics to use when you're training. So I'll just quickly explain what those things are. The optimizer is the algorithm that Keras, remember that library I told you about, is going to use to train your network. And the loss function is how it measures how well it's doing. So initially, of course, the network starts off in a random state and it sucks at recognizing digits. As it goes through the training set over and over, it has to calculate how well it's doing. So say it predicts that it sees a 5 and it thinks this is actually a 2 or an 8 or something similar. It has to calculate how far that is from the actual truth. And that's what this loss function is. And metrics is a similar value. Those two kind of go hand in hand. Next step is kind of the most important, and it's going to be the longest one. It's going to take it a minute or two to run. We call this a function called fit, which means take all of the training data and arrange your neural network, the weights in your neural network, as best you can in order to match the training data. So let me run that while I continue talking because it will take a while. You can see it training here. The loss is hopefully decreasing, which means it's getting better and better at recognizing the digits, and the accuracy is increasing because they go hand in hand. I told it to train for 5 epochs, which means 5 runs through the training data. And in theory, each run through the training data, it gets better and better. But there are things like overfitting, which means that your neural network learned too well to match the training data, which is a whole deep topic of its own. The analogy I'd use is, imagine a teacher teaching the class. People sometimes complain that, oh, they're not really teaching the kids math, they're just teaching them to pass the test. Well, when you overfit a neural network, you're teaching it to pass the test, which means you think you've done really well. You get a great accuracy of like 99%, but then you show it digits in the wild and it sucks because it overfit on the training data. It only learned that batch of training data and it didn't really learn the deeper truths that you want it to learn about how to recognize digits. So it finished training, and at the end, it printed out the loss and the accuracy for us. This is 96%, which is pretty damn good. I'll tell you that in the real world, if we're working on real data sets, we're glad to get 70 or 80%, And if you have an algorithm that improves that by a few percent, like, you're getting pats on the back. Like, this is a really hard mountain to climb. So the reason we get such a great accuracy, this is a toy problem, and it's designed to be sort of ready for neural networks to work on. Real world, obviously things are messy. You get noisy data, you get conflicting data. You never get this level of accuracy. People would be very suspicious if you presented a paper and you said you got this.
Yeah, Daryl, I usually end up overtraining on all of these little toy things, and you get really frustrated because and then I train it and overtrain it, and I beat it into submission, and then it still gets the wrong answer, and then it's
exactly.
time to go off and paint
Darren, my models get over 100%.
I think the current administration would be interested in your models.
I read this article, and it talked about the example where they were training on this medical data, like to recognize lesions or something like that, and they get all done with it, and it didn't seem to do that well. When they actually put it out there, it didn't do very well at all. And they realized much later, unfortunately, that really what it was recognizing was the little ruler on all the medical data.
Yep, I've heard of those.
Yeah.
And there's another one where they were trying to discriminate huskies, the dog, from wolves in images. So they gave it a bunch of pictures of wolves and huskies, and it was close to 100%. And then when they dug in deep, they realized, well, what we've actually built here is a snow detector, because all the pictures of the huskies had snow in the background, and the neural net had detected that. So yeah, 100%, it's a snow detector. So there's a lot of stories like that of overfitting. So you have to be really careful, and there are techniques to avoid that. There's a whole body of research on how to avoid overfitting. It's a constant danger when you're in AI. Hey kitty, yeah, that's a cat, I detected that. So evaluation, yeah, that just prints out the accuracy. We can save the model, which is useful because you don't want to have to retrain this thing. Sometimes training can take like a week. Google have released models that take a month to train. So here I've persisted the model weights. If I were to open that file, it will just look like a bunch of binary garbage. Yeah, I've probably screwed up my terminal now. Anyway, it's just it saves the weights as a binary file. So you don't have to retrain in future. Now we're going to predict on the first few images. We're going to ask the model, look at these test images, which you've never seen before. It's very important. And give me your predictions. So if I print out the predictions, this is an array of predictions for the models. So don't worry too much about this. But remember I told you about that function that converts each digit to a probability that it thinks it's that digit. These are those probabilities. So print out the test labels. This is going to give us the right answer. So our network predicted 72104. I print out the test labels. Why didn't it show? I'll do it in the console here. And it got them right, which is not surprising because it's a toy problem. We got great accuracy, so it correctly predicted those digits. Let's actually look at what those digits are. So in order to do that, I need to reload them. Test images. I'm just going to load those images up again. So it thought the first one was a 7, right? So let's see what we think about that. We're going to say view image test images 0. What did I do? I used the wrong parens again. It's a habit.
I have the same problem.
I should start a support group. So I agree that's a 7. Yeah, I think it predicted correctly. How about the second one? It thinks that's a 2. So let's see if we agree with it or not. Yeah, I agree that's a 2. So there's nothing too wild in this data set. There's no like Dr. Scrawl in here. So it's not surprising that it does well. And last thing, I'm going to do what Garrett mentioned earlier, which is plot the model. So this is a feature in Keras where you can ask it to visualize your neural network. And when I do that, it outputs an image file like this. So if you guys think back to this guy, this is the same thing. It's just printed in a different way. We have our input layer, which is 784 bytes per image. We have a dense layer, which is processes the input and outputs 64 hidden units. magic happens here. This is what we were training to recognize it. And this is the output layer. It takes those 64 units and outputs up to 10, outputs exactly 10 values, which is the probability that it thinks it's each digit. So that is basically it. We're a bit over time here, so I won't go messing with the code and showing you different options like that as I was planning to do. But does anyone have any questions? And please feel free to ask dumb questions. I ask dumb questions all the time. So all questions are welcome.
I have a question, but I'm going to wait until other people can ask.
Sure. Yeah, even if it's like, what's a neural net, or why are those colors on your neural net diagram, or what are those arrows for? Anything.
You have one in the chat.
Oh, thank you. Okay, how do I see chat on here? What would be a good accuracy to aim for? That's a great question, and it really depends on your data set. So for a toy problem like this, I would expect it to be up in the 90s. In my experience in the real world, we're glad to hit 80%. And it often depends on the domain of the problem as well. For example, one customer we had markets anti-aging products. And our neural network would take an image of someone before they use the product, and it would predict what you might look like afterwards, and it would try to estimate what age you look after you use the product. This sounds kind of crazy, but this is the kind of thing we get asked to do in AI. So in that case, if they're advertising claims that they want to be able to knock 5 years off your age visually, well, our network had better be accurate to less than 5, right? Because otherwise we can't back up their claims. So it depends on what kind of domain you're in as well. And say you're in the medical domain where you're looking at images, so I think Michael mentioned this earlier, or somebody else mentioned it, you're looking at X-ray images and trying to predict if there's a tumor in that image. There you'd want very high accuracy. Like no one's going to want to hear, well, we're 60% sure you have a tumor. They want it to be up in the 90s. So it's very much domain dependent. And it's also an ongoing process. So if you come up with a new neural network architecture or a new algorithm, you'll compare that to your accuracy from previous runs. Good question. Anything else?
My question is back to images. Some of the work that I have done there, again, it's working with friends, not in the real world, is that the accuracy of medical images is so bad that we can't actually do much with them. This particularly was looking at skin cancer items, and that the accuracy was so bad. Have you been facing the same thing, that the standards of the data that you're trying to get of images is just too poor?
In our case, no. My team worked on X-rays for that exact problem, X-rays for tumors, and we were getting eventually pretty good accuracies, like up in the 80%. There are even systems that can beat human radiographers nowadays in medical imaging. So yeah, as long as the data set's there. But someone mentioned the tendency to overfit. Like we did have a case where the algorithm learned to figure out which kind of X-ray machine had taken the image. And instead of bothering with the image, it would say, oh, that's a Siemens 1835B machine. And those are only used for really sick patients. So the network had figured out the type of machine that had taken the X-ray and somehow correlated that with sick patients. And it knew that if you're being X-rayed with this machine, the doctors probably think you have a tumor. So it was kind of overfitting and cheating. But in answer to your question, Michael, we haven't really experienced that. And I think the state of the art has really progressed the last few years with those medical images. So we're doing pretty well now, to the point where doctors insist on consulting the AI. Like they have their own idea, but they still want to see what the AI says about the image.
Much like a chess computer that I have. And I think I want to play this. Let's check the hint and see if I missed that long.
Yeah, we already lost that battle. The best chess computers can beat Magnus Carlsen in their sleep. So thank you for that question. Any other questions before I hand it back to Garrett?
I have a question, but I'll pause because I want to give other people a chance. Don't be shy.
Yeah, don't be shy. Feel free to ask any kind of questions.
I mean, I would, for me, just personally, and like I said, I'm a newbie, but just what are the purposes of the different layers and when would you want to use them?
Yeah, so that goes back to the
types of algorithms or whatever,
Right. That goes back to the art. The dirty secret of AI is knowing how many layers to use and whether to use like this ReLU activation function that I had up here, or TANH, or sigmoid, or any of the others. There's a lot of trial and error involved. So people outside of the business think it's science, where you know exactly what kind of network you should use and which kind of layers, but it's not. Sorry, the state of the art is not there yet. So we tend to consider on previous problems, okay, this is an image recognition problem. What kind of networks did we use on previous image recognition problems, and which ones worked better? So we do that. There's also evolutionary algorithms that will help you figure this out, that will help you decide what kind of network and which kind of functions to use. But again, that's sort of an experimental phase right now at best. It's not a solved problem.
Darren, what I have shown in one of my classes was a different problem. I was doing the Titanic data, not images, but just data. And I just built a loop and went through all of the options and all of the different engines, and then evaluated all of them. And I've discovered that I am not the only one who just slams through all the possible images on a smaller set or a smaller, and then tries all the options.
You can brute force it for sure, especially if you have the bucks to spend on AWS or Azure to do it. But even then, it rapidly gets out of control, because there are hundreds of activation functions you can choose from. And how many layers? Well, that's an open-ended problem. Maybe 100 layers would work better. So if you multiply out all those combinations, you're into astronomical numbers, which is one reason that evolutionary search algorithms work better for that kind of thing, because they're good at searching really huge search spaces with high dimensionality. So that's an unsolved problem. If you can figure that out, you probably have some awards coming your way. But right now, the best we do is sort of, what's the word for it? Empirical, guided by previous knowledge, gut feeling. Unfortunately, that's where we're at.
Or maybe we could use the word science.
I think we shouldn't use the word science, because it's not. Science would imply we have some methodology and it's repeatable and people would be able to reproduce it and agree on it. And unfortunately, a lot of AI isn't like that. A lot of it is more like alchemy than science. I mean, it works. It delivers the goods, as you guys saw. This thing learned to do what we wanted it to do and predicted the images. But why did it work because of this? Could we get better results using other things? Like if we put TANH in here, would it work better? Who knows?
Or worse yet, is there a better library that we should be using that has a better
exactly.
Which is what I run into on my on just the strict data stuff.
Oh, totally. Even with Keras, there's different backends you can choose. You can use Tiano or Tensorflow. You can use PyTorch instead of Keras. There's a bazillion different libraries, and they probably all perform better on some problems and worse on others. So yeah, there's a lot. We call it experimentation for a reason. There's a lot of experimentation. And you have limited time, right? You don't have time to try every possible option. So you have to go for what you think are the likely candidates that will provide good results.
Are there any ways to know if you're overtraining? I mean,
yeah, good question.
You don't want to overtrain, but it sounds like that might be something that's really hard to evaluate.
It is, and often when you publish white papers, your colleagues will say, hey, you've just overfit here. So by the way, I just replaced that layer with TANH, and our accuracy was slightly better, 97% almost. It still predicted everything correctly. So who knows? Maybe it just got lucky on that training run. There is some randomness. Anyway, to answer your question about overtraining or overfitting, that's why we separate the data into test images. So these are images that the system has never seen before. We train it using these, the training images, but we test it with these. So these are unseen images. If it had overfit on the training images, it would get a really good score when you ask it to recognize the training images, because that's what it was taught. We taught it to pass the test. But then when we actually give it unseen images, it would suck. So this is one technique. There's also another technique called cross-validation, where you repeatedly train on different subsets of your data and then test it on the unseen subset. So instead of just doing one split of your data like this, you do 10 splits or 50 splits, depending how much data you have, and you cross-validate on each split. And when you do that, it's much less likely that it's overfit.
Yeah.
There's also other techniques, like you can add a dropout layer. I don't know if this is going to work.
Hey, Darren.
I know, time.
Transition into the Q&A if you're okay. Or I mean the poll.
The poll. Yeah. So yeah, I just wanted to add that there's another technique, which is adding dropout layers, which is literally tearing down pieces of your network and removing them. And strangely, this helps prevent overfitting. It's like assassinating random parts of your network, scare the rest of it into not overfitting on the data. I don't know quite how this works, but dropout is another useful technique. You can Google dropout overfitting and learn more about that. So yeah, thank you. Over to you, Garrett.
Thank you, Darren. Not everyone's on microphone, but I'm going to give you a round of applause for sharing. Thank you.
Thank you. Yeah.
Much appreciated.